Human populations. When we study human populations, we can apply the same principles of population biology to human populations. Demographers are scientists who study those changes in human populations. A unifying theme in environmental science are the impacts of an increasing human population. However, as we will see, there has been progress in human population growth. Early human population growth was relatively slow and was only limited by access to reliable food sources. With the event of the Industrial Revolution, these limitations were overcome and the human populations began to grow unlimited. As we found in Chapter 6, populations which are not constrained tend to grow geometrically. The human population is no different, and since the 1800s has shown a J-shaped growth. With that in mind, the question becomes, when will it stop? At what point will humans reach their carrying capacity? It took thousands of years to reach 1 billion people in 1804. It took 150 years to double that to 3 billion in 1960. The increase from 5 to 6 billion took only 12 years. Another way to look at it is that the Earth's population tripled in the 20th century. Will we overshoot the carrying capacity? A timeline of human population exponential growth. Many people feel we will not reach a carrying capacity because technology will find ways to overcome any carrying capacity. This idea is called technological optimism. A better question may be, are resources ultimately limiting on Earth? In other words, is matter finite or infinite? Technology can boost carrying capacity as we make progress in agriculture, engineering, commerce, and medicine. These achievements make it possible to support many more people per unit area. However, much of our growth has been based upon cheap, abundant fossil fuels. Will rising fuel prices constrain food production and distribution? If humans are affecting the population, then the next question is, by how much? This can be calculated using the IPAT formula. IPAT is calculated as the impact equals the population size times the affluence of the society times the level of technology. Since the impact is the product of population size, affluence and technology, people living in developed countries will have more impact than people living in less developed countries. Factors that determine growth. Demography encompasses vital statistics about people, such as births, deaths, distribution, and population size. The current estimate for world population is 7.2 billion for 2013. An educated guess, many people remain uncounted. Some nations overstate or understate their numbers for political reasons. Two demographic worlds. First is poor, young, and rapidly growing. Less developed countries, found in Africa, Asia, Latin America, contain 80% of world population and will account for 90% of projected growth. Second is wealthy, old, and mostly shrinking in North America, Western Europe, and Japan. Average age is about 40. Populations expected to stabilize or decline. Here is a graph that illustrates this information. Table 7.2, the world's largest countries. Ironically enough, while people living in more developed countries have more impacts than those in less developed countries, most population growth is occurring in the less developed and developing countries. Declining population growth can occur for several reasons. In the U.S. and other Western countries, total fertility, the average number of children born to an average woman, has steadily declined. This is attributed to higher levels of female education and more women in the workplace. In other less developed countries, war and disease are reducing life expectancy and increasing infant mortality. The AIDS epidemic has hit Africa the hardest. A map that illustrates the population density around the world. Note that population is not distributed equally around the globe. The impacts of a reduced total fertility can be seen on the doubling time of a population. As total fertility decreases and approaches 2.1, The average number of births approaches the ultimate rate of mortality. Think of a bank account. If you earn $2, the TFR, and spend $2, the parents eventually die, by how much will your bank account grow? This is the approach seen with the idea of zero population growth, ZPG. As the total fertility approaches 2.1, the rate of growth reaches 0. At this point, zero population growth has been reached. Mortality and death rates. Crude death rate. Number of deaths per 1,000 persons in a given year. Poor countries average about 20, while wealthier countries average about 10. Some rapidly growing countries have a very low crude death rate due to a high population of young people. Natural increase. Crude birth rate minus crude death rate. Total growth rate. Includes immigration, emigration, births, and deaths. Even with a TFR of 2.1, a population won't reach zero growth immediately. This is because of population momentum. Momentum occurs because of changes in life expectancy versus lifespan with changes very little. Life expectancy made large strides in the early part of the 20th century and has continued to increase since. However, recent changes in life expectancy have been very small. Contrary to popular culture, increases in life expectancy are not due to changes in medicine, but instead changes in hygiene, sanitation, nutrition, and education. A line graph illustrating life expectancy at birth. Life expectancy at birth is higher in more developed regions. Demographic implications of living longer. A population growing rapidly due to natural increase has more young people than does a stationary population. Even if total fertility rates were to fall, the population would continue growing as young people enter their reproductive age. Population momentum. Some countries now have a stable population with the same number of people in each age group. Declining populations have more old people than young people. This is a graph showing life expectancy versus income. A graph of age structure.